Okay, we will get going. It is good to see loyal students here on the WebEx page on a day like this. I know that your temptation is to put on your shorts and your sandals and whatever and go out and lay down in the grass and just enjoy the sunshine. My thermometer in the sun at my house outside was reading 80, which my wife says that's not 80, it's because it's in the sun. Well, yeah, but it says 80. So anyway, my dogs have been out all day running around having a great time. So maybe spring has finally come to Minneapolis. All right. What I'd like to do today is to go back over. I told you, and I owe you another revised schedule. I added another day for state estimation. It's a big topic. I said earlier that this was one of the features of the state estimator that was most useful is to detect bad data and then identify it. And those of you that took the tour of OSI a couple weeks ago, one of the things that I thought was interesting is that originally when state estimators were contemplated, they were contemplated for the biggest of the systems, which were then called energy management systems. Now the big systems are the independent system operators, which I think I've given you my opinion that the European name, which is transmission operator, is a far better term. I wish we would adopt it here. And so the transmission operator for our region is it's actually called the Midwest, the Mid-Continent, pardon me. It's no longer Midwest, it's Mid-Continent Area ISO, or MISO. So the abbreviation MISO still applies, but the M stands for Mid-Continent now. But one of the things that OSI people pointed out is that even if you're just operating a SCADA system, a lot of people like to have a state estimator. And right here, there's some of the reasons. And then they said that even on those smaller systems, they're doing security analysis. So we're going to see late in this lecture that to do security analysis, you've got to have real-time model of the system. That means you have to have a state estimator. Okay. We would assume that J of x, remember J of x is this sum over all measurements, so n measurements, and it's z of I, that's the measurement value, minus f of I of the state vector x, and this is basically the calculated value for that measurement. So if this is the measurement of a power flow, then this is the power flow that gets calculated from whatever the state vector is, the voltages and phase angles, and we divide that by standard deviation for the measurement. And we square the whole thing. We put a 2 out there so that this thing doesn't matter what the sign is of the upper part here. These equations are power flow equations, so therefore it's nonlinear. And I will let you go through the text and so forth. That we talk about the fact that you end up with a Jacobian matrix and you solve it, and then you relinearize. You recalculate the Jacobian. That's relinearizing. and you solve it again, and you solve it again. And what we're going to see is that J converges, and what we're going to propose is that the magnitude of J is smallest when there's no bad measurements. And we assume that there's also, we treat it just like a power flow. We're going to converge, and when we converge, no more iterations are going to do us much good. But we're going to say that when we have bad measurements, we go through and we go through this process, and I've got several examples to show you today's problem session. And we're going to see that the state estimator gradually gets better and better, and that when it reaches the smallest, it is going to be when the bad measurements are all out. Does it ever get to be zero? No, because this measurement has noise. All measurements have some noise, have some little bit of error for various reasons. So we cannot hope to get a perfect state estimate. Okay, so if that's the case, then the question comes up, what should this be to say that bad measurement is present? How big? How big? And this gets into the whole thing. And fortunately, a lot of this had already been worked out. The statistics for these problems had been worked out, and the mathematicians, statisticians had worked out the fact that J of x has a probability density function. If you haven't had a probability course, you're just gonna have to learn something about this. But this is the function that describes how this thing varies due to the random noise that's inside the measurements, and it has which is called a chi-squared distribution. Now you'll note that J of x is made up of something that we then square, and that gives us this chi-squared distribution. And you can look up tables. There's ways of calculating the chi-squared distribution, and it's abbreviated. That's the letter chi, as best I can do it, and it's got this parameter k. K is called the degrees of freedom. The degrees of freedom. In our case, and at degrees of freedom, it's equal to the number of measurements minus the number of states. And the number of states for a power system is twice the number of buses minus 1. And the reason we end up with the minus 1 is that we have the states are, remember, the states are the voltage magnitudes and the phase angles. So just put an I there. Well, we have NB voltage measurements, voltage magnitudes that we could measure. But for the phase angles, we have NB minus 1 because one of them we declare as 0 degrees. And then we're basically down to looking at the phase angles of all the other buses, and that's our reference or slack bus, whatever you want to call it. Okay, so that's a start, but there's quite a bit of work that we can do on top of that now, so we can say that we will define a threshold T sub k such that when j of x is greater than T T sub j. Don't you love this? I can just color it in. Okay, T sub j. Here we go. Okay, when it's greater than T sub j, then we have a bad measurement. And but this is sort of an well, what value? The question that comes up here is okay, what value? What value do we put on that T sub j? And the problem is that if we put T sub j that's too small, then we get many false alarms. Okay, too small. Well, it says if I put a very, very small number on it, and I say j has to be, if anytime j is less than 10 to the minus 4, then we have bad measurements. It's going to say bad measurements every single time because j is not going to get down to be that small number. So we have to, you have to be realistic around that. On the other hand, if we put j that's too large, then what happens? Then it says, I like to do it this way, it says all is well most of the time. It says all is well, everything's okay. If I put a very large, so that I say, j can be anything up to, 2 million. Well, it probably will never even get that high. So you'd say, there's no bad measurements. All right, I'm picking two stupid extremes here. So what we'd like to do is to work out a formal way, means of picking T sub j, and that's what we're going to do. And we do is we say, okay, well, what is the probability that j of x? Remember, j of x is a scalar; it's a single number, and it's random because the measurements have random noise. So therefore, it's random, plus it may have bad measurements. So the probability that it's greater than T of j, given, and this they always write it that j of x is chi squared with k degrees of freedom, DOF, okay, equals alpha. Now, so all I did is pass the buck. That's an American expression that means I didn't really make a decision. I just kind of said I'm going to pick something else. But it's a little more rational for the choice of alpha. What I'm going to do now is I'm going to say, well, I would like to say that I'm going to pick an alpha, okay, and I'm going to say I'm going to pick alpha, and really what is done. That, by the way, let's label things here. This is called the significance level. The significance level, and this whole process is called hypothesis testing. And we say for a given alpha, then we can get T sub j. Well, alpha is a little more rational because we're saying, well, the probability of a false alarm A false alarm means that it says there's a bad measurement when there isn't. That's probably something we want to be careful of. We certainly don't want to be. We don't want to be saying, "Oh, then just pick some alpha so that we don't get any alarms." Okay, that's the wrong side. We want to work on this side of the thing. The probability of false alarm is equal to alpha. So you make it a small value. And obviously you're gonna play with that value, but you're gonna experiment with that value. You're gonna say, okay, what is the probability that suppose I set the probability to a certain number, like I'll use an example for 0.1. I'll use it 0.1. So let's say let alpha equal 0, 0.01. Okay, that says 1% of the time I'll get a false alarm. That's 0.01. So if I run this state estimator 100 million, millions of times, 1% of the time I get a false alarm. Assuming that you've got to always go back and say, assuming this holds, okay? Assuming J of X is chi-squared like we said it was. And that in turn assumes that the measurement errors are normal and that they are normally distributed as per sigma. Now, believe me, there's been a lot of work in this area. There's a friend of mine who is at Virginia Polytechnic, and he did some very, very good work. He is a real, honestly, a statistician who knows the statistics, probability theory far deeper than me, and he did a lot of work on that. He said they're not normal. You will find out after a while in life that that sometimes people that there are certain things that you do, that you choose certain parameters or certain distributions because you can make the theory work. One of them is to always pick a normal distribution. Once you do that, everything follows. If you try to do it, you say, no, it's really a two-part distribution and it's not even smooth, you're going to have a very difficult time doing the analysis. All right, let's just forget that for a minute. But this is roughly says 1% of the time I'll get false alarms. Otherwise, I'm not. And this is good now. So the thing that we want to concentrate on now is the following plot. Here is the value of J of X. Now we know it isn't going to be 0. And so we're going to plot on this axis, and I'm going to just tilt the paper here. You'll get your notes whenever I scan this. The probability that J of X is greater than T of J given J of X is chi-squared with k degrees of freedom. All right, it's the same assumption. So what's the probability that it's greater than T of J? Okay. Well, if I pick a T of J that's 0, the probability is what? Is absolutely 1.0. Here's 1 right up here. There's 1. And so it goes over 1 like this, and then eventually you get a large enough. And so this is I'm gonna put a T sub J value out here someplace, and then this thing will tell me what that probability is. Well, it turns out that if you get to k here, then this number is 0.5, which I didn't draw very well, and then it just keeps going down and down and down like this. If I get J, if I set the T to a great big enormous number, then the probability would come down to 0. Okay, so this makes sense. If Tj is 0 or a very, very small number, the probability that j is greater is 1. It's always going to be greater. As it goes out larger and larger, this number comes down. And let's say that right here is 0.01. So this will be our T sub j. And this is I'm drawing this large here. But there's our gap of 0.01. Really, is this I'm sorry. This is 0.01. This is alpha. There's the gap in there is alpha. Okay. No, I didn't do it right. I'm sorry. This is alpha out here, and this is T sub j. This is T sub j. Let me just draw this in here. This is Tj. Okay, alpha 0.01. Then this is the Tj. This is the resulting Tj. If alpha gets very, very, very small, so does Tj. Okay, so I can now say for our power system, and let's take our 6-bus system. It actually has, you can see this in the textbook, the number of measurements is 62. The number of states is equal to 2 times the number of buses minus 1, or 2 times 6 minus 1, which is 12, minus 1 is 11. Okay? So K equals 62 minus 11 over 51. Okay. Well, it turns out now that if I pick alpha of 0.01 out here, this Tj, I said this would be Tj, and that turns out to be 63.44. That's the resulting value that you get with an alpha of 0.01 and a K, a degrees of freedom of 51. Okay, this J, the shape of this depends on K, on the value of K. So if K is 51 and I set alpha of 0.01, then T sub j is 63. So what we're saying then is that if j of x at the end of converging the state estimator, if this j is greater than 63.44, then we have bad data. Now this is the so-called detection problem. All I've done is I've said there's something bad out there. I haven't said where it is or what it is. If j of x is less than 63.4, then we have a very high probability, that up to a probability of 0.01, that there's no bad data. And you might sit there and say, well, suppose it comes out 63.5 or 0.45 or something. Now you're getting into the realm where you have to go down into the statistics and so forth. And you say, well, look, we're setting this threshold, and as you get closer and closer to the threshold, the truth is that we'll see later that our state estimator comes out way out in the thousands, and then when we take the bad data away, it comes back and it comes way down underneath that 63 value. Okay. I ran in the book. I ran the state estimator, and I took a P plus JQ measurements, which was 123 for the P, and the Q was minus 35.6, And I changed this to minus 123, and I changed this to plus 35.6. And when I did that, just one measurement, so there's actually, this counts as two measurements. Two measurements are bad. Now, it's a P and Q measurement require that we be measuring voltage and current. And we're measuring the voltage and current. Okay, and so if the current measurement, for example, is off, both the P and Q values are going to be bad. So that's why basically you lose two measurements when you when one of them is bad, the other one will usually be bad. In this case, with this bad measurement, J of X was 6,455. I mean, a 1,000-fold increase over the 63, which is obviously much greater than 63.44. So we can assume that it's bad. Okay, so we do indeed have bad data. All right, and I'm going to show you these cases, but I want to show you the rest of the theory. And the rest of it, the theory gets more difficult. There's something called a normalized residual, and for that calculation, you're going to have to look at some of the references. But I don't think it's that important that you know. Now, how do you identify the bad data? Okay, the first step said the first setback said detect the bad data. Once it's detected, now we want to identify. If we say, hey, our detector says there's no bad data, well, I'm not going to go off and try to identify it. I'll just say, fine, move on, do the next step. Okay, so here's we'll say here's my meter, that's the Z value, and here's the true value. Maybe it's some P flow. That is the thing, because Zi ends up being the true value plus noise. Well, this is a random variable. This thing here is a random variable. So this thing is giving us noise. This thing ends up with, and if we assume that the noise is a normal variable, then we get values that bounce around. They crowd around, and they're if it's a really high quality measurement, the noise is very small. Then it'll bunch right around the true value. But we get values that are never hit the true value all the time. They're different. They're scattered around. Okay. Now, if we then said, well, remember, Fi of X is the estimate of Z, is the estimate of that quantity being measured, and I get some other thing here. Now, I drew this with a little narrower, so better. It's better. The optimal is when this collapses to a line. Well, it gets thinner and thinner. Why would the estimate of Z be better than just the Z itself? And the reason for that it's better is because we have many measurements which help to calculate Z, which is really F sub I. F sub I. So an experiment is to, and this is the kind of thing you do in basic probability courses or statistics courses, is you say, look, I'm going to say, I'm going to have you all go out with some measuring device and measure the same thing, a certain distance or an angle or a voltage or something, and then we're all going to come back and we're going to write down all the values that you got. And then I'm going to say, well, now what is the estimate? And the best way to do the estimate, if you took a bunch of measurements, they're all random, they're all completely uncorrelated. In other words, the error on one has nothing to do with the error on the other. You just take their average. You take the average. So you take the average value of all the measurements. And it turns out that the sigma for the average is smaller than the sigma for any one of them. Let's assume that all these measurements had the same error, but obviously they're different devices, so they're all getting about the same. If you take many of them, it squeezes in. So Z ought to be better. So here's one reason for using the state estimator, is that if you put lots of measurements out there, well then you should be able to say that you know the value of certain measurements. You know the value of the measurements better than you would by just measuring it with only 1 meter. Okay. And so then we're going to form what we call the residual, which is y sub I is z sub I minus fi of x. Now you recognize that this is going to minus sign in here. This is what's inside my definition of J, z minus f. Okay. And so this ought to have, because they both are going around the same true value. So then the average error should be 0. So I can plot this one around 0, and I can say, well, I have this residual. Now remember, I'm taking the difference between Z, which has a certain distribution, and F sub I has a certain distribution. But we're assuming that they're both centered on the same value. That's what I had up here, the same value. Well, if I do that, then I come out with 0, and I have a certain sigma I. Okay, and it's good to call that sigma yi, which is the sigma that you can calculate knowing the sigma for Z and the sigma for this. And then what you do is you say, well, I'm going to create what's called the normalized residual, which is yi over sigma, or it's zi minus fi of x divided by sigma I. Okay? Sigma y sub I, pardon me. This is y sub I. And if I just do that, then this has a distribution that's normal 0, 1. What does that mean? Its mean is 0, and the sigma equals 1, because I've divided it out. Okay, so I have, finally then I have a distribution that looks like this. Now the nice thing about this, N01, is that we know that here's sigma, here's 2 sigma, here's 3 sigma. Okay, 3 sigma sub yi. Okay, now what I'm going to do is I'm going to assume that probabilistically I can say that anything that's within plus and minus 3 sigma, there's a good chance that that's considered good. And so anything that's outside, I can draw the other side. Here we go. Here's 1, 2, 3. Here's minus 3 sigma. And so anything that's out here is bad. It simply says that the probability that it's going to fall outside of 3 sigma is very small. And again, this is predicated on the idea that my z has a certain measurement error sigma, and therefore I can say if I get a value of my normalized residual that's way out at 10 sigma, well, that's something wrong. There's something wrong. I can't help but say this, and someday this will probably come back. There's a whole theory that General Electric for a long time used to talk about 6 sigma, and as having that their idea was to say that the number of bad devices, we're going to do quality control, and we're going to say here's 6 sigma. That only devices that we're only going to allow devices to go out to our customers if they're, that they have to, that the 6 sigma is the threshold. In other words, we're going to do quality control until it just hurts. That's an excellent goal. It's an excellent thing to do. I won't go into whether you can actually get the 6 sigma, but driving your company to more quality is good. Is very, very good for your company. Let me very good for your customers as well as for business, because it means you're never going to have faulty products. Okay, so that was their idea, 6 sigma. So again, there's the definition of yi normalized, so we'll call it norm, is z minus fi of x divided by sigma yi. And if yi norm, is greater than 3, we assume that measurement is bad, and if yi norm is less than 3, we're going to say it's okay. And what we're going to do is we're going to calculate sigma yi for every single measurement, and we've solved this with the state estimator. We know what z is. That's the value. So we take the difference, divide it by the normal, and then say, well, what is the yi? Is it greater than 3? Kick it out. If it's not, we're okay. We're home free. Okay. Now, what I'm going to do today is get my test cases out. And I will start, first of all, I want to show you this. This is in the manual that's on the CUSP site. I want to repeat something. Use the programs that I give you on the class Google Drive site, not the programs that are out on the CUSP site. I am doing special things to certain files for the sake of this class that are not out there, and probably someday I should go back and decide whether or not I'm going to put all the changes out on the CUSP site. But don't use it, because a couple times people have gone out and they've pulled the CUSP site, and I've pulled them in and I've started working on it, and lo and behold, there's a bug. So I fixed the bug, and everything runs perfectly. I put it on the Google Drive. One of the students comes along and says, when I run it, I get this error. And it is most likely that they're using what's on the CUSP site. So for the OPF homework, I gave you 2 different directories with all the programs and data files in them. Use those. And then for the state estimator homework that's going to be posted Friday, again, go get the files off of the Google Drive site. One last, obviously this is something that, if you log on to the mail system, which is Gmail, I realize, but if you log on with anything but the university, your university email, you will not be able to get to the Google Drive. I keep getting people saying, I need to get into Google Drive. I need to get in, and my answer will always be use your university email so that you can then get into it. In a couple cases, I'll be very honest, a couple cases, I don't know who it was. If they were a student or not. The email didn't correspond to anybody that I knew. It was a Gmail address that I couldn't even read. It was characters from another language. So I just told them they have to be a student. All right, so there's really three aspects to the state estimator thing. I have network data files out there, and we're always going to use our 6-bus case, okay? So this is just simply the network data. And it's the same 6-bus case file that we use for PowerFlow. And we run a PowerFlow. And we store in the output, we store a binary file which has all voltages, phase angles, P flow, Q flow, etc. It calculates the whole output. At the same time, it prints it on the MATLAB working pane there. But it stores it in a binary file, and then it quits. And there's a program. If you want to do it in the simplest way, there's a very simple program. Yes, it is. It's called Run All, and Run All will call the PowerFlow. And then it will call something called the SCADA, and then it will run the state estimator. And I'm going to show you in a minute here that what happens is it runs the PowerFlow, and then it pauses, and there's a message that comes on that window. On my computer, I have the MATLAB editor on the left. On the right side of the screen, and I have the window, the working window, or whatever you want to call it, for the MATLAB on the other side of the screen. You've got to have your cursor that you're using. Grab your mouse and put the cursor over in that working window, and then whenever it pauses, and it'll say, hit any key when you want to get going. Then if your cursor is over there, put it on that side, tap it once, and then that establishes where then you just hit the return key and it'll do it again. So it pauses so you can look at the screen and you touch the return button, and then it goes and does the next step. Well, the next step is the SCADA function. Now SCADA has measurement data out here. There's a separate set of spreadsheets that define the measurements. Go look at them. They're very simple. They say, okay, I've got a voltage measurement on bus 1, 2, 3, 4, 5, 6, an angle measurement on 1, 2, 3, 4, 5, 6, and then it says I've got a flow measurement on, and it goes through all the lines in the system. I've got an injection measurement on each of the buses, and so forth and so on. All the possible measurements. And the idea is that the SCADA system says, and I'll just draw this over here. It says I've got, let's see, we're at 5 here. Suppose I've got a flow out here from bus 1 to 2. I don't know what the actual, but let's say that it's reading 12.6 megawatts. Okay, this is the actual. Then the state estimator says, okay, the SCADA system, and what a real SCADA system does, By the way, that stands for Supervisory Control and Data Acquisition. Supervisory control is the ability of people to send a coded message to the substation to open a breaker or to change a transformer tap, to control something. Data acquisition is just go out and read something. So it goes out and it reads. Read the M12. This is M12 measurement, and it gets this 12.6 value comes back into the SCADA system. So that's now in your computer. So now it associates 12.6 with M12, and it's really the P portion of whatever M12. So it tells the computer, I went out and read this value of 12.6. Note, if you will, that this is the true value. I could make a joke here and say nothing to do with the hardware store, but anyway, most of you wouldn't get that. Some of you will. It is not. It is the true value, 12.6. So one of the things I can then do inside the SCADA system is add noise. And I have a little random number generator that looks at the sigma for the, and it might take 12.6, and it adds noise so that whenever the SCADA gets done, it says, oh, that measurement is 13.2. There's an error. I added an error. Okay, I added an error of what, 6.6 onto there. So this is the measurement. That is the measurement as received. Okay. And it's the true plus the noise. That's all you got. You don't know the true value. You would like to know it, that you're trying to estimate the true value. But so the SCADA system, now in the real world, that noise is added inside the process, and then whenever we transmit the value, we don't change it in the SCADA system, but I have to do it someplace. So the SCADA now hands off. And the measurement file, the measurement Excel file, okay, tells me where all the measurements are and what the status of the measurement is. If the status is 0, it says that measurement's not in there. It's not working today. It's out, and it tells me the sigma, the expected quality of the measurement, okay? And it also displays the measurement data. The measurement data is displayed. All right, so now it hands off another. I'll go back to the diagram here. So here's the power flow data, and here is the measurement data. There's the measurement data in another binary file. And now there's a couple other things that I have provided for it before I run the actual state estimator. And I have the ability in here. So the things that I can do, I can add noise or not. Or not. Now sometimes you want to say, what does it look like if I don't put noise in there? And I think maybe for homework I'll have you do one with and without noise just to see what it looks like. But normally we want to see it with noise because that's the real world case. I can also edit any measurement. I can edit a measurement. Now if you want to turn a measurement off before the whole process starts, you go back into the spreadsheet file and change its status. But what you can do here is, if this is where, like if I had that measurement before, which was what, minus 123, and I changed it, I edited that to plus 123. The editing is simply a way of testing the state estimator, making some of them bad. So this is really where you make it bad. make a bad measurement is in here. And that all takes place in here. And whenever you click something, you get these nice little windows that come up. Unfortunately, when I capture it on the screen, I don't capture now I can show you. This is from the manual. I'm going to put this section in here, but here's an example of when SCADA comes up. It says add noise, edit measurements. You can edit measurements over and over and over because you may want to do a different measurement, a different kind of measurement, whatever. When you're all done, it says store the measurement data and exit. So this is the one that says, okay, store it all away and go on to the next step. Okay. Here is the edit screen. Edit a voltage, edit an angle, edit an injection, edit a flow. Get out of the editor. And the editor is pretty simple. If you're going to do a voltage measurement, it says, okay, here's the voltages, and here's the voltage, the bus number, and here's the actual measurement value. One of the things that you guys will learn someday in writing software for power systems is that the data doesn't come to you with buses 1, 2, 3, a continuous set of numbering up to the thousands of buses. They skip all over the places. They say, well, the first 300 buses are our company, and then we're going to start our neighboring company's bus numbering at 1,000. So there's this big gap in the bus numbers, and you've got to write the software to accommodate that. I don't even think we put that in here, but that's why we said the measurement number and the voltage, the bus number. Okay. So this is the measurement number and the bus number. Measurement number, bus number. And these are the measurements over here. All right, so then you go to the state estimator, and the state estimator has two choices. Do you want to detect bad data? And the answer is yes, we will always do it. If you're testing something out, you can skip that, and it'll just do the estimator and quit. Okay, it won't do the looking for bad data. So here's the first run that I make, and I will put all of these cases in the notes, so you'll get a copy of this today. And what I'm sorry about, I got to keep looking at the screen because if I start talking about something down on the bottom, you won't see it. So you start it, and here is the data file. I always have it print the data file out so I know what it was using, and it converges. Notice that this looks like a power flow. It's got a maximum delta P and a maximum delta Q. It's just like a power flow, and it converges. Here's where it converged. Well, I'm sorry, this is the power flow. But what we're going to see is that the state estimator, when the state estimator runs, it is similar to that. This is the power flow. So here's the power flow convergence. Power flow converges, and we get our standard power flow. We get the bus data, the flows down here, okay? And at the end of that, you notice that it says, it says pause. When you are ready, hit the enter key. You have to take your cursor. So here is the cursor. You just put it over here. Here it is. It's, I don't know, on my screen I have a cursor that's a big fat arrow like that. Make sure it's on this screen and you tap it once. Otherwise it won't read it. If you leave it in the editor, if you leave the cursor over in the editor or some other, it's got to be in this window. Then when you hit return, the program says, oh, you're done looking at this. I'm now going to continue running the programs. Now, so then it asks you to put the measurement data file. The spreadsheet. I purposely put a page break here so that we wouldn't be coming to the bottom and having to flip over to the next side. So here's after the page break. Here's the second page here, and it says here's the measurement numbers, and I've got my own measurement identification system. MV is a voltage measurement. MA is an angle measurement. MG is a generator. ML is a load, and MIJ is a flow measurement. And we assume that these are always P and Q flow measurements. So here's the base case value. This is true up here. This is the true value. The true value. And here's the measured value. Okay. Now, in the middle of this, once I started the SCADA program, so this comes here as the SCADA, and you notice here it says noise added. So I put noise in, and so you can see that there's some slight differences. 246.1. Well, it says the measurement that there's a slight noise, and so that's 244.6, and they're all slightly different. Okay. Now this one has all the measurements except phase angles. If there's no phase angle measurement here, then it doesn't use it. So I didn't put it in there. And that just tells you this is what we had for all the measurement data. So this is the printout from SCADA. Okay, and again it stops, and you put your cursor down here and hit return, and it starts going, and it gives you that thing. It says, do you want to do bad data detection or not? Now I didn't purposely put any bad data in here, but here is the first execution of the state estimator. It starts out with J of 26,616. That's starting from the voltages and phase angles are like 1.0 and 0 degrees, and then it converges, and so that it converges to 73.713. Unfortunately, the TJ value for us, remember 63.44 when I had all the measurements in, it's 63.4. This thing is telling me I didn't do anything, but it says you got a bad measurement. So the program says, okay, now we're going to do, and we're going to calculate the normalized residual for all the measurements and just pick the worst one. So it picks the M51, which is the line from bus 5 to bus 1. M51 is right here. So the measurement itself is 97.3 and 19.1, and it gets 106 and 23. So bad measurement. And it kicks it out. It kicks one measurement out at a time and runs it again. Well, now it comes back with 62.18 and 61.2. So it converges. It can start with the previous solution. However, the degrees of freedom have changed because I dropped two measurements, right? So I dropped two, so I'm down to 49. So this number goes down. I've got to get a little better, and it's just slightly over. So you could say, oh well, call it a day and just wash your hands of any. But no, we're going to kick out the MV5, the normalized residual. Notice the normalized residual here, 2.92. This one is 2.7. They aren't exactly 3, but they are the largest, so we're going to kick them out. So what did I say? MV5. And MV5 is up here, 233, and it came out 228, so that's bad too. Okay, and when I did that, when I kicked that one out, this thing converged down to be 53, and I'm at 60. My j of x, right, my t sub j value. This is the t sub j value right here, is 60. And then you can go back in. Well, let's look, for example, at the M51 is 97.3 and 19. This is the measured value, the base, the measured, and the estimated. Okay, so here's my terrible bad measurement. Once I've kicked that measurement out, look at this, 97.1 and 17.8. It's predicting it. Same thing with the voltage here. 228, it's got this, it says that the estimated value is 239. Now this one is amazing. This one is amazing, people. If somebody wants to try to explain that to me, that one, it got worse once I kicked the voltage measurement out, and it doesn't come back again. I'm not using the measurement. That's probably why. But that's the process. So then the next thing I did was, let's see, we get time to get all through these. So then I took the thing, I ran the power flow again. Remember, I'm doing run all. And so it runs the power flow again, and then it stops, and then you hit return, and it starts up again. And this one, I'm only using measurements on bus 1. Measurements at bus 1 only. No other. See, there's no other measurements. So it's going to have to put pseudo measurements in, and it's just got some pseudo generator values, and then it doesn't use it uses one load value that it's got. We'll assume that it has these from some historical database or something. So it put some pseudo values in there, and when it runs this time, it converges the TJ, because I've only got 4 degrees of freedom. My TJ is 6.9. It converges literally to 0, at least a number less than 000. So it's less than 10 to the minus 4. So it just converges, and it's perfect the first time. Boom, there's all the estimate. And if you go back and look at this thing, by golly, I only had measurements at one substation. I used pseudo measurements elsewhere, but the state estimator was able to figure out all these measurements, all these measured values. They aren't measurements. See the zeros for the measured? But it got values here that are essentially equal to these. Again, the beauty of the state estimator, you can lose a lot of measurements, and unless you lose observability, you'll be able to predict what's going on in the power system. So it helps to be reliable. Case 3, run the power flow again. Noise added, and in this case, what am I doing in this case? I've got measures at bus 1 and 2. 1 and 2, so there's no pseudo measurements. Nothing down here. So when I solve, once again, the TJ that it's shooting for, it has to make is 16, and it gets to be 12.4. So it meets our test on the first try, and says there's no bad measurements. So that's just to show you there's no pseudo measurements in that case. And I've got a couple more cases to show you here. Case 4, run the power flow. Now, I decided let's really mess around with this thing. So I said, okay, I told it I want to do the injection measurements, and so it says here's all the injection P and Q values. I said I'm going to do it at bus 4. I'm going to mess around with bus 4. So it says here they are. They're and you put the new values in. Well, you see plus 4 is minus 99 and minus 16. So I put plus 99 and plus 16. So I'm going to say backward measurement, meaning things are negative of what they should be. And then it parrots back to me and says, okay, this is the value of the measurements, you know, and then it says you can go on. That's all I did. I told it, and so this was at bus 4, and this is the injections at bus 4, minus 99 and minus 16. So here's the measured value. This, I confess, this should be telling me that the measured value is plus, not minus. That might be an error, but it does take the positive value and throw it in there. And it says if you're all done, then you run the estimator. So I run the estimator. Remember 63.44? Well, I get 3,000. I've got bad measurements. So it goes right after ML4. That's the load measurement on bus 4. That's the one we put in error. It took it out. And now it's going to shoot for 63, and it ended up with 66. So there's a line flow that it comes up with that has a very, very small error. This is only 60, it's a 3.1. Remember I said this is the normalized residual. Look at this, 54. Okay, it's not even close to 3 sigma, and forget the 6 sigma. It's out at 54 sigma. Okay, well, that's ridiculous. Throw that out. This one, it's near 3, but we throw it out and we get 58, and the test is this comes in at 56, so it makes it. And here's the estimate. The last case that I did for you that we will, if I don't drop it on the floor, case 5, ran the power flow, and then I took injection measurements at bus 6, and I just took them and I said 98 goes to 150. Minus 150, and minus 18 goes to minus 40. And then I took a flow measurement, or a different injection measurement on I'm sorry, no, I took a voltage measurement on bus 2. Instead of being 1.03 per unit, I put 1.4. So this is the measured value, and so I said that's a bad measurement. And then I took a flow measurement, which was number 10, which was from 4 to 2, and I changed that around too. So I've put a bad injection measurement, a bad voltage measurement, and a bad flow measurement. And I ran the state estimator. Boom. The first time it ran, it converges to 3,595, and it says the M42, that's a flow, has got a huge sigma, so take that out, rerun it, and now I'm down to 693, but that's still pretty bad. Take out this voltage on bus 2, and now I'm shooting for 61, and I've got 693. Then I'm going to take out the load on bus 6. That measurement is bad, and once I take that out, I make it so that the estimator solves. So we are at the point where you know, and your homework will consist of running some cases like that, along with some other problems in the state estimation realm. I want to now lecture very quickly. I want to just go over the fact that the state estimator will tell you if you have bad measurements, and you correct the bad measurements. What do you do? So what? What do you do? So here we have a SCADA system, and it gets all these measurements through the communication system, and it runs the state estimator. And out comes the voltage and the phase angle. And we also have that we put into the system, so we now have a model of the system. And if you look in the book, one of the things that SCADA brings in is breaker status. And the breaker status says I've got to build the buses exactly the way the breaker status is set up, and so that if I have a breaker like this and it's between two buses and it's open, well then this it comes out to be two electrical buses. Maybe there's a line attached to each side, and so these now have two lines, but they're two separate buses. If it was closed, actually, we'll do it just a real SCADA system. A closed breaker is red, so we'll put it in red. Okay, open would have been green. Hey, I've got colored pens here, so so this is open. This is closed. And if it's closed, then we get a single bus, and we have to basically change the model. Okay, they often call this model a breaker bus model for that reason. Now, when we have the voltages, we have this represents the what is there on the system. What's actually happening on the system. And this is a model of the real system. So you take these, and you can now start running security analysis. You know what that is. Let's spell that right. Security analysis is running outages to see if what will cause problems on the system. You can run an optimal power flow if you want to see the best way to dispatch the system, if you're going to use the whole model. So the state estimator provides you with the initial model to use for security analysis and OPF. Okay, and then if security analysis gives you and says you got a problem over here, then there should be a way of going out to the power system and correcting something. For example, we'll see later on another lecture, going out and changing the dispatch so that we change the transactions across the power flowing across the system. Will get rid of that security problem. Okay, so that's what the state estimator is basically all about. Bad data detection and identification, estimating quantities that we don't actually measure, and using it to initialize our model for security analysis. Okay, state estimation is another one of those things. The first paper, you're going to begin to think that I was always there at the beginning, but I was there at the first paper that Fred Schweppe presented in 1967. Okay, that makes me old. I agree, it makes me very old, but Fred Schweppe produced this, the very first state estimator paper in 1967. It, again, took years and years before really, really reliable state estimator algorithms were available. But by the time we went to deregulate the system, we had working state estimators, working security analysis, working optimal power flows. Just put it all together. That's all we needed. Okay, so I have a big pile of paper to scan in and give you for your notes today, and we will go outside. It's only 5:15. It's still sunny. Probably it's not 80 degrees anymore, but it's nice and warm. You guys that are from countries that used to be in the British Commonwealth, you can all go out and play cricket, right? I know that for many of our students from India love to play cricket. You see them around the campus. There's actually a park near the town where I live, Hopkins, Minnesota, My son says that when he goes over to this one part of the park, there's a bunch of fellas from India that are out there playing cricket in the summertime. They love to play cricket the way we Americans love to play baseball. So go out and have a nice cricket game. Enjoy yourselves. Okay, spring has come. Alrighty, so we'll see you all on Thursday. We will not be on state estimation anymore. We will be on a new topic, okay? So I'm going to leave the meeting and say good night to all of you.